Hi, in this lecture we will be talking about eigenvalues and eigenvectors. We already established that multiplying a square matrix A, which is of order n by n, by a vector x of length n by 1 will give us another vector, and this vector will be of the same size n by 1. So we established that A is transforming the vector and producing another vector of the same size. In many scientific problems, the following question arises. For a given transform represented by a matrix, is there any specific vector in space that will not change its direction under this transform? In other words, if you have some specific vector, and this is your vector x, and you're transforming it with multiplying it by matrix A, will the result be on the same line? So this is a question that we are asking. Surprisingly, this same question is asked in such diverse applications as system stability analysis, image compression, big data, dimensionality reduction, clustering in machine learning, or even in Google PageRank algorithm, which is used by Google for selecting the correct pages for you. So let's formulate that question in more mathematical way. What we want to find is the following. Let's say you have matrix A multiplied by vector x. So as we said, this one is n by n, this one is n by 1. And we want to find such vector x and such constant, which we'll call constant lambda, which by multiplication by x, which is the same x, will give equality here. So this is a question of eigenvalues and eigenvectors. In other words, multiplication by some constant lambda of some vector x is just moving that vector point on the same line. For example, if lambda is less than 1, but more than 0, then the vector will be just shorter than the original vector x, so it will be somewhere here. If lambda is larger than 1, then the result will be somewhere here of multiplication of lambda by x. If lambda is negative, then the result will inverse the direction and the output will be something in the negative direction but on the same line. So this is what it means to multiply scalar by vector. Now, clearly matrix A can rotate or scale or do all kind of other manipulations with the vector x. So our question is, what kind of vector x is that for a specific given matrix A, we will have, after multiplication by matrix A from the left, we will have basically vector on the same line as it was before. And we clearly can generalize it to any number of dimensions, and the line will become hyperline. Let's see if it is even possible. So we want to rewrite it a little bit, and we will get something like that. Ax minus lambda x equals to 0. Now, we know that we can multiply any vector or any matrix by identity matrix I, which is the diagonal matrix of 1s, and everything else is 0, and it will not change the matrix or the vector. So this is similar or equivalent to Ax minus lambda multiplied by I multiplied by x equals to 0. Because lambda multiplied by I multiplied by x is the same thing as lambda x. Now, this I can write as A minus lambda I, just combining the terms of x, multiplied from the left by x. Pay attention that this is matrix n by n. So I still can do that. And this one equals to 0. Now, what we can say about that matrix, let's call it A tilde, which is A minus lambda I. This is the initial matrix A. So if this is matrix A, and we have some elements on the main diagonal, so we just took and some other elements on some other places. So we're just taking the main diagonal and from those numbers subtracting lambda, minus lambda, minus lambda, whatever it was, minus lambda on the main diagonal. This is what we basically did. And this is our matrix A, tilde. Trivial solution of that is very basic. So x equals to 0. This is trivial solution. Clearly this solves that equation, but this is not that interesting because it's not giving us any interesting information. Clearly vector 0 you can rotate in any direction or scale in any direction, you still will get vector 0, and this is obvious. But are there any non-trivial solutions to that equation? Because we are looking for non-trivial solutions for that kind of equation. And this is what we want to do here. You learned already that this will have non-trivial solution only if the matrix A tilde is invertible, is not invertible. Which means A tilde not invertible. If it is invertible, you have only one trivial solution. But if it is not invertible, then you might have multiple solutions to that system of equations. Pay attention that from the properties of determinant, you also know that this matrix is not invertible only when the determinant of this matrix, which is that of A tilde, is 0. And it's equals to that of A minus lambda I. And this is the formula for computation all of the lambdas, which will provide solution to that system. And this is what we want. Also note that this is a polynomial of nth order, and it has lambda variable. It should have n complex or real roots. So from here, you will get polynomial like lambda to the power of n plus a n minus 1, lambda n minus 1, and so on, until you get to a1 lambda plus a0. So you will have all kinds of coefficients from a n minus 1 to a0, and this polynomial will be equal. From here you will have roots of that polynomial lambda 1, 2, 3, and to n, which belong to complex or real numbers. Now we are ready to define eigenvalues and eigenvectors. So lambda 1 through lambda n are eigenvalues. Of the matrix A. Now, for the solutions of that equation, x will be the eigenvectors which are appropriate to the eigenvalues of that system. Now, let's write that formally. For each lambda I, the solution of the equation A multiplied by xi equals lambda I multiplied by xi is the eigenvector xi of matrix A. So any vector xi which will satisfy that equation for a given number lambda I, it will be eigenvector of the matrix A, which is appropriate to the eigenvalue lambda I. Now note that you will have infinite number of that kind of vectors which will satisfy that condition. We will talk later how you normalize those vectors to give it some unique value. But here you should have infinite number of solutions to that system of linear equations. Otherwise you have some mistake in the computation. Let's start with a simple example of 2 by 2 matrix. And this matrix is given by 1, 2, 0, and 3. And we will find eigenvalues for that specific matrix and eigenvectors. So, I remind you that first of all you need to solve that kind of equation, which will be polynomial equation, and let's see why this is polynomial equation first. So you are looking for determinant of, inside you have matrix A, which is 1, 2, 0, 3, minus lambda multiplied by 1, 1, 0, 0 matrix, which is matrix I. So let's simplify. So the first element minus lambda multiplied by the first element here will be 1 minus lambda. Second element minus lambda multiplied by 0 will be just 2 here. 0 minus lambda multiplied by 0 will be 0. And 3 minus lambda multiplied by 1 will be 3 minus lambda. So this is a determinant that we need to compute. And by definition, this determinant will be 1 minus lambda multiplied by 3 minus lambda minus 0 multiplied by 2, which is just 0. So this is 1 minus lambda and 3 minus lambda. This one equals to 0. So 2 roots of that polynomial equation. Of course you can open that and to do lambda square and so on. But from here it's much easier to see what are the roots. The first root is when lambda equals to 1, and second root is when lambda equals to 3. So lambda 1 equals 1 and lambda 3 equals 3. Those are the eigenvalues. Now, how we find eigenvectors now? We need to solve the following system of equations. So it's 1, 2, 0, 3 multiplied by some vector x. And this vector x, we can say, let's say, xy or alpha beta, whatever. So some unknowns. And this one equals to lambda 1, which is 1, multiplied by the same alpha beta. So from here you have system of equations. Alpha plus twice beta equals lambda 1 alpha equals to alpha, since lambda 1 is 1. Now second one is 0 multiplied by alpha, 3 multiplied by beta equals lambda 1 multiplied by beta, and this is also beta. Now pay attention that from the second equation beta has to be 0. And if you put that beta 0 into the first equation, you get alpha plus 0 equals alpha, which is always true. So alpha could be any number you want. From here, you conclude that your vector will be, eigenvector will be the first one, which is corresponding to eigenvalue 1. It will be just something like 1, 0. So this number could be anything, and this number has to be 0. So it could be 2, 0, 5, 0, 75, 0, minus 5, 0, whatever. But this is just one representative of that vector, and this is eigenvector number 1. The second one you find the same way. 1, 2, 0, 3. Two unknowns equals lambda 2 multiplied by the same two unknowns. And it equals also, since the second, this should be 2 of course. So second one is 3. This is what it should be. So from here you have system of equations. And the system of equations is alpha plus twice beta equals 3 alpha. And the second one is 3 beta equals 3 beta. So the second one is trivial, so beta could be basically anything you want. And from the first one, you're saying that 2 alpha equals 2 beta. 2 could be cancelled. From here, alpha equals beta. And from here, your second vector equals, it could be just any numbers where alpha equal to beta. So let's say 1 and 1. It could be 2 and 2, and so on. So this is the second eigenvector. So this concludes the computation of eigenvalues and eigenvectors for that specific matrix. Now, let's try some other example, and we will try to find eigenvalues for the matrix of rotation. So I remind you that rotation matrix is cosine theta minus sine theta minus sine theta and plus sine theta and cosine theta. So this is a matrix. And we will try to find that r minus lambda I equals 0. So let's say that we get determinant. As before, we get cosine theta minus lambda, and here it's minus sine theta, and here we have sine theta, cosine theta minus lambda, and this is what we want to compute. So it's cosine theta minus lambda squared minus sine theta multiplied by sine theta with minus will be plus sine squared theta. So let's simplify a little bit. Okay, let's see what we get here. So we get cosine squared theta minus twice cosine theta multiplied by lambda plus lambda squared plus sine squared of theta. So pay attention that cosine square plus sine square will give us together some 1, because cosine square plus sine square trigonometric identity, it gives you 1. So you can write that as lambda square minus twice cosine theta lambda, so it's polynomial in lambda, and plus 1. And this should be equal to 0. Pay attention that this is quadratic equation in lambda. So let's find the roots lambda 1, 2 of that quadratic equation. So it will be minus that part, which is basically twice cosine theta, plus minus square root of the determinant divided by 2a, which is 2. So it's b squared inside will be 4 cosine squared theta minus 4. So this is how you compute it. Now pay attention that this 4 and this 4 can get out as 2 out of the determinant. So you can remove it from here, you can remove it from here, and you'll have 2 here, 1 multiplied cosine minus 1. Now pay attention that cosine square minus 1 is basically from the same rule like here, that sine square theta plus cosine square theta equals 1, then cosine square minus 1 is basically minus sine square. So this thing is minus sine square of theta. Now pay attention that sine square is always positive, or at least not negative, which means that if you take in square root of it, it's square root of negative number. Now 2 also could be cancelled here, here, and there, which means you can remove those 2, this 2, and this 2, and then what is left is cosine theta plus minus square root of minus sine square theta. But square root of minus sine theta is basically j multiplied by sine theta. So you can remove all of that and to write j sine theta. And pay attention, what is that? You can write by Euler identity that this is exponent of j theta. This is our eigenvalue of that rotation matrix, e to the power of j theta. This concludes that example. One more important thing that I want you to learn about eigenvectors is how to normalize them. Essentially, you can normalize any vector. So if you pick in some vector v, the idea is that you want to get to some other vector v tilde, which will have size 1. And size 1, by size 1, I mean that it will have norm v tilde, which is equal to 1. This will produce basically unique vector, unique eigenvector for you instead of infinite number of possibilities. And pay attention that most of the packages like MATLAB and other sophisticated packages for computation of eigenvalues will produce for you only specific eigenvalue. And this eigenvalue will have norm equal to 1. So how you get from just general vector v to a normalized vector with size 1? Because after all, you care only about the direction of the vector and not the size of the vector. So vector with norm, if you have some specific vector v, you want to have only unit vector which has norm which is 1. So how you compute that? This is a transform, it's very simple. You convert from v vector into v divided by norm of v. This is what you do to find vector with norm equal to 1. Now, why this vector has norm 1? This is a question. Let's see. This is a proof. You want to prove that norm of the vector v divided by norm of v equals to 1, always, no matter what vector v is. Now, let's see why is that. Of course, this is for v not equal to 0, then the norm is defined not as 0 divided by 0. So for any other value, it will be 1. Why is that? Look, 1 over norm of v is a scalar. So you can write that the following way. It's norm of 1 divided by norm of v. This is just some given number multiplied by vector v. So it's scalar here multiplied by vector here. And this is a norm. Now, from the properties of norm, we know that we can take scalar number out of norm with absolute value, which means I'm taking absolute value of 1 over norm of v multiplied by norm of v. This is from the properties of the norm. Now, pay attention that this number is definitely positive. So 1 over that number, which is reciprocal of that number, is also positive. So I can remove basically absolute value here. So it's 1 over norm of v multiplied by norm of v. So they both cancelled, since both of them are numbers. And this equals 1, as I promised. In conclusion, one more step might be necessary to get from the eigenvectors that you've got from the computation on the previous slide to eigenvalue which is given by MATLAB to you. This is how you get there. You just divide it by norm of that vector and you get that number, that vector.